An important issue when designing a feedback controller is always how do I define the values for the proportional part, the differential part, and the integral part of my controller. In this video, a number of methods will be proposed. Detailed information about most methods can be found in the relevant videos in this playlist. First of all, let's start with motion control systems. They are often defined in the frequency domain. And we start with a system which looks like this, which is consisting of a motor which drives a load over here through a flexible transmission, which could be a transmission belt. And in this system, we have a position controller and we have a system feedback on the motor shaft using this encoder over here. And when we have that situation, we have a so-called system with a anti-resonance resonance behavior. And for that system, for that kind of behavior, you can use the loop shaping rules. And these loop shaping rules are explained in the video Motion Control Tuning Loop Shaping. So again, it's a motor driving a load through a flexible transmission with feedback by using an encoder on the motor. Now suppose that there is not a flexible transmission between your motor and your system because it's really a tight transmission or the load is coupled directly to the motor. In that case, you can use loop shaping rules for a single mass system. And I have a video in this playlist called Loop Shaping for Dummies, which explains how you can tune your controller when you have that kind of a system. So again, for motion control systems, designing your controller in the frequency domain is really a very good option for getting a really good performing controller and taking all stability aspects into account. Then there is the S domain, and in the S domain you could use pole zero placement methods, and the method which you use in that case is based on the root locus. And what you are doing in that case, I'm not so familiar with it, is that you place dominant poles determined by the time domain behavior like overshoot and settling time, because these overshoot and settling times, when they are based on a step response, determine where your dominant poles might be in your system and what the forbidden area should be. So starting rules could be that you define the integral time constant as the largest time constant of the process, and for the D action you can define the time constant of your derivative action of your differentiator to the second largest time of your process constant. Alright, and then there is for low-end controllers the time domain tuning methods. And there are a couple of tuning methods which you can use when you really want to use a low-end controller or when you are starting with control systems. Then it's always good to start with these kind of tuning rules. And important tuning rules which are really familiar to a couple of people, a lot of people I should say, are the so-called Ziegler-Nichols rules. There is a video also in this playlist which discusses the PID Ziegler-Nichols tuning rules. Ziegler-Nichols defined two tuning rules. One is based on a step response, based on a first order process with a delay, and then you have the oscillation method. So that is really a nice tuning rule for again starting with a controller and a low-end application. When Ziegler-Nichols cannot be applied, for instance, the system cannot get into oscillation or it doesn't have a delay, well, then you have a so-called happy-go-lucky way tuning method. And then you could say, well, when I have an integral controller, I put the time constant of my integrator on the largest time constant or near the largest time constant of my process. I define the time constant of my derivative action, so my D controller, in the neighborhood of the second largest time constant. And if you want to make a lead filter, you can define the pole of the lead filter to the D action 0 divided by 9. And then you can adjust the gain of the proportional part in a way that, for instance, you don't have any overshoot. Alright, so that is really a starting method when all other rules are not applicable. Don't forget, when you are tuning your controller, check always your performance because it's always on performance, not only the stability. So, for instance, you have requirements on the response time, you should check that, or what the settling time will be. Check that and compare it to the requirement. Is overshoot allowed? Could be a question, or which disturbances have to be suppressed and to what level. What might be the tracking accuracy, or what is the requirement on static error, and so on. So check the performance in your time domain. Check, of course, stability. Is your system stable and is it stable enough? That's really important. And always, I should say, always use feed forwards when possible because that is information you often have when you have a good model and it's really easy to use feed forwards. When you don't know exactly how it works, please look to the appropriate video in this playlist. And when you have to implement it in a digital controller or in software, then use approximation techniques for the Z-domain implementation. So you could look to, for instance, Tustin's rules or the other rules there are, but Tustin is a really good one, or the backwards approximation rule. All right, and don't forget, have fun, and remember you're in control. Have fun, make a lot of nice controllers, and yeah, as I said, you're in control. Bye bye.